Hello everyone. Welcome to the session. Today we are going to learn about what is conservative force and what is non-conservative force and the law of conservation of energy. Let us see first one, what is conservative force. What is conservative force? For conservative forces, path independence can be interpreted to mean that the work done in going from a point A to point B is independent of the path chosen, and the work W done in going around a simple closed loop is 0. Simple closed loop is 0. See here, that can be mathematically written as W is equal to closed integral f of r dot dr equal to 0. See, especially in this field, if you are going from point A to point B, some work is done, right? When the force is applied on the particle or object, when it is moved from point A to B, some work is done. Then after, when the particle moves from B to A, some work is done. If the work done is independent of the path, then the resultant work from A to B is equal to from B to A, and the total resultant work will be 0, right? So in this, it is path independent. Conservative force is nothing but it is path independent. The work done in going around a simple closed loop is 0. W is equal to integral closed integral f of r dot dr equal to 0. Let us move further. Next, see here, the total energy of a particle moving under the influence of conservative forces is conserved, in the sense that a loss of potential energy is converted into an equal quantity of kinetic energy, or vice versa. See here what happening there, the total energy of a particle moving under the influence of conserved forces is conserved, in the sense that loss of potential energy is converted into equal quantity of kinetic energy, or vice versa. See, we know that energy converted into potential energy to kinetic energy, and kinetic energy to potential energy, depending upon the situation, right? Already told you, when the aeroplane is in the sky, it has potential energy and as well kinetic energy. But when the aeroplane is on the runway, when it is running before takeoff, when it is on the land, it has, when it is running on the land, it has kinetic energy, there is no potential energy. But when that plane is in the sky, it has potential energy, that means some height from the ground, then the potential energy written as mgh, and also its velocity, kinetic energy is of mv square, right? That is addition of total energy, addition of potential energy and kinetic energy, we got some value. But when it is on the land, it has only kinetic energy, we have some value, both values are same if it is conserved field. Okay, right. Let us move on to another one. Next, what is non-conservative force field? See there, non-conservative forces are dissipative forces such as friction or air resistance. Non-conservative forces are dissipative forces such as friction or air resistance. These forces takes energy away from the system. As the system progress, the energy that you can't get back. These forces are path dependent. Therefore, it matters where the object starts and stops. See here, non-conservative forces are dissipative forces such as friction or air resistance. See, everywhere all are non-conservative forces because there is friction between the layers and also there is air resistance. Due to these factors, the resultant work may be varied certain extent. So that is the case of non-conservative forces. If you consider whole the system, if you, for example, if ball is rolling on the floor, if you consider only ball, we'll get loss of energy. But if we consider whole system, ball along with the floor friction, will get total energy remains constant. That means it is conserved force. Consider there friction force also. Okay. So this force takes energy away from the system. As the system progress, energy that you can get back. Due to the friction, what happened? System lost some energy in the form of heat, right? Some energy is uh, lost by the system. And these forces are path dependent. Yes, in the previous case, in conservative, forces are path independent. They depend only initial and final position of the particle. They independent on the path. But here, non-conservative forces are path dependent. Therefore, it matters where the object starts and stops. For non-conservative forces, the path dependence can be interpreted to mean that the work done in going from a point A to point B is dependent of the path chosen, and that the work done in going around a simple closed loop is not zero, right? So in that case, W is equal to closed integral f of r dr is not equal to 0. Okay, so next conservation of energy, law of conservation of energy. Let us see here law of conservation of energy. Where law of conservation of energy, the law of conservation of energy states that we know very well, this is fundamental law. Energy can neither be created nor be destroyed, only converted from one form of energy to another form. See that energy neither created nor destroyed, it's converted from one form to another form. In a closed system, that is a system that is isolated from its surrounding. What is closed system? It is isolated from the surroundings. The total energy of system is conserved. Conserved means no change in its energy. Whatever changes takes place inside the system, inside the closed system, but the total energy remains constant. Total energy remains same. Conserved means no change. So energy cannot be changed. Whatever changes occurred inside the system, inside the closed system, right? In a closed system, a system that is isolated from its surroundings, the total energy of the system is conserved. This means that a system always has the same amount of energy unless it is added from the outside. See there, for example, see there, here, this means that a system always has the same amount of energy. For example, if you take a system, something is happening inside the system, some maybe changes takes place inside the system. Whatever changes takes place inside the system, energy is same because it is a closed system. Due to the collisions, due to the friction, whatever changes takes place inside the system, energy remains constant unless it's added from the outside. if the system absorbs energy from the outside. Otherwise, if something is given energy to the system, that energy may be varied. That is not conserved system. Okay. Here the condition is system should be closed system. Understand? Next, examples of conservation of energy here. See here examples. When fuel is burned, see here, when fuel is burned, chemical energy is converted into heat and light energy. See there, when fuel is burned, chemical energy is converted into heat and light energy. Right? If you take any fuel, if you take wood, if you take papers, if you take petrol like fuels, if you burn that material, whatever material you take, then what happened? Chemical energies, some chemical process occur, and which is converted into heat and also light energy. We'll get light as well as heat. Next, second point. In a loud speaker, take loud speaker, what happened in that case? Electric energy is converted into sound energy. Right? Electric energy is converted into sound energy. Now third one. If we take a torch light, so what happening in torch light? We put their cells inside the torch light. Without cell, there is no light coming out. So that means what is happening? If we take cell inside the torch light, chemical energy of cell is converted into electrical energy. Chemical energy of the cell is converted into electrical energy, which is converted into light and heat energy. Right? We'll get some heat from the torchlight. We'll get light from the torchlight due to the chemical reaction takes place inside the cell, inside the battery. Okay. Next, in generators, fourth one, in generators especially, in generators, mechanical energy is converted into electrical energy, right? Some mechanical energy is converted into electrical energy. Now, few more examples are given there. In hydroelectric power plants, see what happen in generally hydroelectric power plants. So we store water in the dam. Water falls on the turbine from a height. Water falls on the turbine from a height. So what happened? It results. What happened? This in turn rotates the turbines, generates electricity. Right? We know that large, big size magnets are there. Between these magnets, the turbines will rotate. As a result, which gives AC alternative current will be generated. Hence, the potential energy of water is converted into kinetic energy of the turbine. What happened? Potential energy of water is converted into kinetic energy of the turbine, which is further converted into electrical energy. See there? Potential energy, initially water stored in the dam, some height from the ground. It contains potential energy. For example, water tank on the house, it contains potential energy because it has some height from the ground, mgh, which is converted when the water falls on the turbine. Immediately turbine starts to rotate. That means what happening there? Potential energy is converted into kinetic energy, and further this kinetic energy is converted into electrical energy. Right? This is one example of conversion of energy one form to another form. And again, chemical energy from food is converted into thermal energy when it is broken down in the body and it is used to keep it warm. Right? If we take some food, some type of food, the heat is generated inside our body. What is happening? Chemical energy is converted into thermal energy. It gives some energy to us. Okay, so now we are going to see mathematical explanation of conservation of energy. Okay, so get ready for class. We'll start class now. Hello everyone, welcome to the session. I am Srinivas. Today we are gonna see conservation of energy. So, in this topic, we are going to see total energy of the system is conserved. Total energy of the system is conserved in conservation field. In conservation field. Now, for this, what we have to do? We have to prove that total kinetic energy and the potential energy, sum of kinetic energy and the potential energy is constant. We have to prove this one. Total sum of kinetic energy and potential energy is constant. Now let us see how can we solve this one. Now let us assume the motion of particle in conservative field. The motion of particle in conservative field. Conservative field. What type of field I am assuming? Conservative field. Now let us see if F bar is the force. If F bar is the force acting on a particle. If F bar is the force acting on a particle, now that force is displaced the subject or particle distance distance A to B. From distance A to B. Now what I am doing? I am applying some force on the particle. Now this particle is moved from A to B. Now the resultant work done on the particle. Can be written as like this. See here, W equal to integral. Now the starting and final positions of the particle is what? A to B. Integral A to B. That means what we are doing? We are going to find out total work done on the particle throughout the journey from A to B. So A to B, and already we know that how can we write work done? W is equal to scalar product of force and displacement. Now we have to write there F bar dot d r bar. F bar dot d r bar. So this is the resultant work. Now we have to solve this one. See, how can we write F according to Newton's second law, rate of change of momentum, right? What is force? Rate of change of momentum, dp by dt. So how can we write momentum? Momentum can be written as P is equal to mv bar. Now substituting here, then we'll get m into dv bar by dt. M into dv bar by dt. Now let us assume this is equation 1 and this is equation 2. This is equation 1 and this is equation 2. Now again let us see how can we define velocity. Velocity can be defined as v bar is equal to rate of change of displacement. That can be written as dr by dt. So from this equation what we get there? So dr bar is equal to v bar into dt. Dr bar is equal to v bar into dt. So assume this is equation number 3. Now substitute 3 and equation number 2 and 3 in equation 1. See there what we get substituting all these two equations in equation 1, then what we get there? W equal to integral A to B, and in place of F bar we have to write m into d v bar by dt into dr. Position vector is what? V bar into dt. So this one cancel, and mass is constant, writing outside, and integral A to B, and we have the term V bar into dV bar. And we know that integration of x to dx. How can we write integration of x to dx? Integration of x dx can be written as x square by 2. Integration of x dx is equal to x square by 2. Now applying that law, what we get there? W is equal to what we get here? M into, and this can be written as v square by 2, and here we'll get points AB. Finally we'll write W is equal to M into 1 by 2 VB square minus 1 by 2 VA square. Now W equal to 1 by 2 of M VB square minus of M VA square. So this is the resultant equation. So very important equation for us. Resultant equation and very important equation. The work done by a force on a particle. The work done by a force on a particle is equal to change in its kinetic energy. This is called work energy theorem. This theorem is also called work energy theorem. The work done by a force acting on the particle is equal to change in its kinetic energy. Change in its kinetic energy. This is called work energy theorem. Work energy theorem. This is called work energy theorem. W is equal to of m VB square minus of m VA square. So this is the work energy theorem. Again, this is equation number 4. Equation number 4. Okay, right. Now let us see here. Now if force F bar, if force F bar is a conservative force, then already we know that if F bar is a conservative force, how can we write curl of F bar? Curl of F bar will become 0. Curl of F bar is equal to 0. If any vector is a conservative, then we can write curl of that vector is equal to 0. Then del cross F equal to 0. So this can also be written as F bar is equal to minus del U. F bar is equal to minus del U. F bar is equal to minus del U, where U is called potential energy. Where U is called potential energy. Potential energy, where U is called potential energy. See, this can also be written as this equation. F bar is equal to minus I cap dou U by dou X. Dou U by dou X. So similarly minus, otherwise you have to take minus common, and J cap dou U by dou Y. Dou U by dou Y. Similarly K cap dou U by dou Z. Dou U by dou Z. And the next thing is, but the position vector, how can we write position vector here? So R bar is equal to I cap X, J cap Y, and K cap Z. And similarly from this equation, d r dash equal to, how can we write this one? I cap dx, J cap dy, K cap dz. So assume here this is equation number 5. Earlier we assumed the equation 4, and this is equation 5, and this is what? Equation 6. Now from equation 5 and 6, see there, from equation 5 and 6, see there, how can we write? F bar dot dr bar. F bar dot dr bar. So how can we write F bar dot dr bar? Minus I into dou u by dou x plus j into dou u by dou y plus k into dou u by dou z dot, here we can write dot, here we can write I cap dx plus j cap dy plus k cap dz, and we have dot product between them. So finally, after taking dot product, what we get there? F bar dot dr bar equal to F bar dot dr bar equal to, we get minus of dou u by dou x into dx, dou u by dou y into dy plus dou u by dou z into dz. So this is also equal to F bar minus dr bar is equal to minus du. Assume this is what equation number 7. Equation number 7. So from equation 1, we know that what is equation 1? W equal to integral a to b f bar dot dr bar. Substitute 7 in 8. So what we get there? Sorry, substitute 7 in 1. 7 in 1. What we get there? So integral a to b, and you have to substitute minus d. So what we get finally? W is equal to minus, right outside, and a to b du, and we get there minus ab. Finally we get minus ub plus ue, where w is equal. So this is equal to, assume, equation number 8. So that is the number equation 8. Now, so already we got equation number 4. What is equation number 4? Equation number 4. From equation 4 and 8. So what is equation number 4? W equal to 1 by 2 m vb square minus 1 by 2 m va square. So what is the equation number 8? Let us equate equation 4 and 8. Equation 4 and 8. So what is that? Minus ub plus ua. So equating these two equations, what we get there here? See here, of m vb square minus 1 by 2 m va square, that is equal to minus ub plus ua. So readjusting this equation, what we get here? 1 by 2 m va square plus ua. So that is equal to 1 by 2 m vb square plus ub, and here we can write this one as Ta, that is what? Kinetic energy at point A, and here we can write Ua, potential energy at point A, that is equal to Tb plus Ub. So this can also be written as T plus U equal to constant. T plus U is equal to constant. See, the sum of kinetic energy and potential energy is constant throughout the motion of particle from A to B. Wherever the position you take, that is that the total energy of the system is always equal to constant value. For example, if you take here point A and here point B is there, right? Now if assume point C here we'll get a T plus U value, some value that is constant. If you take here D, point D, here at this point kinetic energy, sum of kinetic energy and potential energy also constant, both are same. both are same values will get. So somewhere it may be potential energy more than kinetic energy. Somewhere kinetic energy is greater than the potential energy. So whatever it is, total energy remains constant. That should be in conservative field. That should be in conservative field. So in a conservative field, if a particle move from A to B, in the conservative field, if a particle move from A to B, if a particle move from A to B, the sum of kinetic and potential, the sum of kinetic and potential energy remains constant. Okay, the total energy of the particle in same at all point, this is called conservation of energy. See there, if you move from A to B, we have some energy. If we move from B to A, we have some energy, total energy remains constant. So especially in conservative field, the work done on the particle is independent of path of the particle. The work done on the particle is independent of path of the particle. Therefore total energy remains constant. If it is non-conservative field, the total energy required to move from A to B is may not be equal to move from B to A, may not be equal to from B to A. So therefore what happens, how can we write WAB may not be equal to WBA. WAB may not be equal to WBA. So this is all about conservation of energy. So for example, if we take aeroplane, if aeroplane is in the sky, so what happened? Let us see. If the aeroplane is in the sky, for example, assuming, so if it is moving in the sky, it has potential energy and as well as kinetic energy. But the total energy remains constant. Kinetic energy plus potential energy is constant. Okay. So now what happened? So if this aeroplane is landed, on the ground, it is still in runway. If it is still in runway, in that time there is no potential energy. It has only kinetic energy. At the time, the total energy is equal to kinetic energy of aeroplane. In this case, total energy is equal to kinetic energy plus potential energy when the aeroplane is in the sky. But when the aeroplane is on the runway, at the time the total energy is equal to the kinetic energy, but the total energy remains constant always. So this is all about conservation of energy topic. Okay, thank you very much.